What's up, guys? My name is Jack. I'm a third year ECE major at Wayne State, and today I'm going to be running through a couple of much more difficult even odd proofs because most likely this is what you're going to see on exams. You're not going to see the simple ones you've seen in examples. They're going to be much more conceptual. So let's just hop right into it. Prove that the sum of any even collection of odd integers will always be even, and then they just give a little more clarification on what they mean by that. So we need any group of even group of odd numbers to be even, and conceptually you can see it's true. You can count out really any amount of even number of odd numbers in your head. 3 plus 3, 6. You know it's true, so we know we can prove it. But right off the bat, nothing immediately jumps out at you. So let's just put down what we know. Assume we have an even collection of odd integers. Okay, from here we can say, okay, how can we rewrite this phrase to be more helpful? How can we make it more so in terms of variables so we can actually do something with it? So we could also write this as 2ki plus 1 dot 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 up to 2kn plus 1. This is our integers. I wrote that wrong. This is this phrase written more so in words and is in integers and is even. Okay. So now that we have this is much more tangible. We can do something with this. We can make this work. So this next step I'm going to jump to isn't actually necessary, but I think the proof makes a lot more sense and is a lot clearer if you do it this way. So we have a sum. We are adding some even amount of odd integers. So we can write this in sum notation up to n I equals 1. And here I doesn't really matter that much. Ki plus 1. Also need to mention where ki, or just k. Ki to kn are all independent integers. And we need to mention that because the integers in this question have absolutely no correlation to one another. It could be 3, 3, 3, 3. It could be all just threes. Could be 7, 3, 7, 3, 13, 17. The numbers have no relation to one another. So we do need to make that. We need to mention that. Anyway, back to it. This, we can, as you know, split that. So we can also write this as ni1 2ki plus an entire new sum, same bounds and everything, but it's just I. And light bulb should immediately be flicking in your mind because you recognize that this is just n. It can be written as just n. And for this one, we can pull out that 2. And there should immediately be alarm bells going like crazy in your mind right now because we're close. We are very close. Now remember, n is even. So n equals 2j, j in integers. Now we can rewrite that expression from before as 2 sum of up to n I equals 1 of ki plus 2j. And now, of course, as you might expect, we can factor out the 2. R equals 1 ki plus j. And now we know that everything inside here is an integer, so up to n, this is in the integers by closure, or you can say axiom of integers, doesn't actually matter. And now, since we know that it is some integer multiplied by 2, we can say 2 sum k1 ki plus j is even by definition. And now with that, we have all the information to say with confidence that therefore any even collection of odd numbers or odd integers is even. The box. There we go. Okay, problem 2. Prove if n is an even integer and m is an odd integer, then this whole mess is also an even integer. And right off the bat, you've probably disregarded a direct proof just due to the sheer ugliness of this mess. But I want you to actually take a step back and say, okay, is it possible? If you think about it a little harder, can you write it as a direct proof? And the answer is yes. You can also solve it not using a direct proof, but the way I'm going to show you is a direct proof because I think it's interesting. So right off the bat, assume n is even and m is odd. This implies n is equal to 2k, k is in the integers, and m is 2j plus 1, where j is in the integers. Now, in this situation, it will be very helpful to rewrite that whole mess with the powers condensed. So n plus m multiplied by m minus 3 to the 16th power. And that is equivalent to, if we substitute in those values, 2k plus 2j plus 1 multiplied by 2j plus 1 minus 3, so 2j minus 2 to the 16th power. And from here, what I want to do is I want to start to unravel this center part, because remember, we can split powers over multiplication. So if we can find a multiple of 2 in this, we can split the power over the multiple of 2 and create a by even by definition type situation. So this is equal to, when we unravel the center, 4kj minus 4k plus 4j squared minus 4j plus 2j minus 2 to the 16th power. Okay, And as you can see, everything has a factor of 2. Okay, so now we can rewrite as 2 multiplied by 2kj minus 2k plus, oh, did not mean to write that, 2j squared minus 2j plus j minus 2, and I'm not going to bother simplifying that because it's not necessary. Anywho, we can then rewrite this as 2 to the 16th power multiplied by this whole mess to the 16th power to 16. And now we can split this power again so that it's 2 multiplied by 2 to the 15 multiplied by 2kj minus 2k plus 2j squared minus 2j plus j minus 2 to the 16th power, and that's all multiplied by 2. Now, since we know everything in here is an integer, let's just put that down. 2 to the 15th power times 2kj minus 2k plus 2j squared minus 2j plus j minus 2 to the 16th power is an integer by closure, but I'm just going to say axioms of integers. And now, since we have that, we can say with confidence that 2 times 2 to the 15 multiplied by 2kj minus 2k plus 2j squared minus 2j plus j minus 2 to the 16th power is an even integer by definition. Therefore, now what we were trying to say, therefore, if n is an even int and m is an odd int, n plus m multiplied by m minus 3 to the 16th power is even, and thus it is proven. Okay, last proof. Prove let n be an integer and p be a positive integer that's less than 3 or less than or equal to 3. Prove that if n to the p is an odd integer, then n is an odd integer as well. Right off the bat, you're probably thinking the same thing I am, that contrapositive is going to make this a lot easier. So let's just start with consider if n is even, then n to the p is even. Okay, so let's get into it. This implies n is even, or more accurate to say assume n is even. It doesn't necessarily imply it, but it's not that important. Anywho, this actually implies that n is equal to 2k. K is an integer. Okay. And from here, it should immediately be clear that this is going to be an exhaustive proof, because the fact that we only have 3 values to check. You could do it by cases as well, but each case would really just be evaluating a number, and there's not really enough steps to that to really warrant, in my opinion, doing it by cases. It would be much easier to just simply say, hey, when p is this, it equals this. It's odd, it's even, that's the end of it. So we are going to start setting up for that. So we have, since np is equal to 2k to the p, since n is equal to 2k. Now consider p is equal to 1. This implies that 2k to the p is just equal to 2k. And 2k is an even number by definition. This is the definition of an even number. Okay, moving on. Now, consider p is equal to 2. This implies that 2k to the p is 2k squared, which can be written as 2 multiplied by 2k squared, and 2k squared is in the integers. So this implies that 2k squared is even by definition again. And now, last value. Now consider p is equal to 3. This implies that 2k to the p is equal to 2 multiplied by 4k to the third. Once again, 4k to the third is in integers by axiom of integers. Did I mention that up here? There we go. By axiom of integers. So, since the center part is an integer, that means that 2k to the third is even as well, by definition. Now, this implies by exhaustion that if n is even, n to the p is even. And now, since we have the exhaustion part done, we can skip straight to therefore by contraposition. If n to the p is odd, then n is odd. For p is less than or equal to 3, and p is a positive integer. Thus it is proven. And I didn't actually need to include this extra information because it is actually, this statement is actually true for all positive integers. And it can actually be proven for all positive integers. It's actually, I'm going to do it now. It's actually very straightforward. So, same case, we're still starting with contrapositive for that. So, what was the contrapositive? Yep, if n is even, then n to the p is even. So if n is even, then n to the p is even. And this whole first part is going to look the same. So assume n is even. This implies n is equal to 2k. K is in the integers. And now, this is where we're going to start to break off a bit. So, well, this first part is going to be the same. We can write n to the p as 2k to the p. Now, this is where it really starts to break off. Now, we're going to need to remember what we did for the last problem with breaking up powers over multiplication. Because we're looking for, remember, the 2 multiplied by some integer. So we can rewrite this as 2 to the p multiplied by k to the p. But we still have a problem, and that is this exponent. It's just, in the definition, it has to just be 2. We can't have any exponents. We can't have anything like that. So, once again, we can use we can cleverly manipulate power properties. So we can write it as 2 to the 1 multiplied by 2 to the p minus 1 multiplied by k to the p. And we're allowed to do this because when you multiply numbers with different exponents with the same base, you just add them. So this is still just 2 to the p. And this is an integer because p is, didn't mean to do that. P is 1 or greater as given. P is a positive integer. So larger or equal to 1. So that means at its lowest, this 2 to the p minus 1 is just 1. And that's just k to the p. And k is also an integer. So 2 to the p minus 1 times k to the p is an integer by the axioms of integers closure. And so, therefore, this implies that 2 times 2p minus 1 multiplied by k to the p is also in the integers we don't need to know that it's in integers. That's not relevant. It is even. That's what I meant by def. It is in the integers, but that's not very relevant. Therefore, now, once again by contraposition, if n to the p is odd, then n is odd, thus it is proven. And I just left out the extra information because it is implied that that is also still true. And that is it for the proofs I wanted to show off today. I hope this has been helpful for you. And I do want you to remember that this is most likely what proofs on exams are going to look like. There's a very low chance that it's going to be something easy like, if 2n plus 3m is even, then n is even and m is even. It's most likely not going to be like that. I don't actually know if that's true or not. I just guessed. But I'd like to wish you good luck in your exams. Hopefully they go well, and hopefully this video has been of use to you. Thank you for watching.